The picture that Antoine showed of Olivier, Antoine, and myself around the year 2000, I don't remember the exact year.
Before COVID.
Oh, the picture was taken later, right?
The picture is on the roof of the
Yeah, no, so, but the work, the GPS work, so that was, I think I spent a month here one summer in Paris, and we were struggling. I mean, I learned a lot from Olivier and Antoine, and we were struggling through this problem, which no one else seems to be interested to at that time. And Antoine showed some of the results in his talk today. And today I'm going to, and at that time, so this was 2000, yeah, I don't think anyone imagined that those results are connected to black holes. And many of those formulae that were derived, in particular one specific formula that Antoine just derived, starting from Green's functions of interacting fermions, I will basically derive that starting from Einstein's equations. And so there's a deep connection between what we were doing then and that, and seeing that connection unravel has been certainly extremely exciting over the last 2 decades. All right, so I'm going to, discuss statistical aspects of strange metals, which is, of course, a very familiar topic that Antoine has already introduced. But this first lecture will be about black holes and the stat mech of black holes, something certainly in the year 2000 I knew nothing about. And I don't expect there are experts in quantum gravity here. If there are, that'll be good because they can help me out. I'm going to give you my understanding of the theory of quantum black holes. And really, if you look at the history, there's kind of 2 major significant developments. One was, of course, the calculation of, proposal first by Bekenstein that black holes have an entropy. And then the computation, I mean, the story goes that Hawking didn't believe it and went out to do a calculation to prove Bekenstein wrong and found that Bekenstein was correct. In fact, that argument apparently took place at the Les Houches summer school. So after Les Houches, Hawking went home and found that Bekenstein was correct and actually computed the exact value of the entropy and the Hawking temperature of a black hole, from which we had the idea of Hawking radiation. So that was all done in the early 70s. Then there was a lot of work following that, trying to understand it better, but at the level of the semi-classical calculation that I'll describe today. And not much happened until, of course, there was, in string theory, realization of certain black holes, which turned out to have a great deal of low energy supersymmetry, where some aspects of Hawking's results were verified. And so that was by Strominger and Waffa. And there were many subsequent developments following those. But the string theory solutions of black holes are for supersymmetric black holes. And they have certain special features, which maybe by next lecture I will be able to describe. And it's not the generic situation that Hawking was thinking about. In fact, the generic situation is realized by the SYK model for certain types of black holes. That's kind of what I'll describe in the first 2 lectures. Okay, but today will be really something that almost entirely is about black holes. So I'm just going to I'm going to redo the original Hawking calculation, well, not really the first calculation, but there was a subsequent paper by Gibbons and Hawking, which set up the problem and did it. And I'm going to go through their calculation, simplified, of course. And as you'll see that the calculation is, involves a lot of guessworks and what seemed like dubious steps. It almost seemed a miracle they got the right answer, as we understand it today. I think even today there's many basic questions about it that are still open, subject of a lot of work. And the SYK model is playing some role in addressing those questions. All right, so So let's begin with this. So if you have, what do we mean by statistical mechanics of any quantum system? You assume you have some Hamiltonian. Then you take it to finite temperature, and then you define the partition function, which is a trace over some set of states of this Hamiltonian, and this gives you the partition function. And in condensed matter, we know what the Hamiltonian is, and so we go ahead and evaluate this by any method we would like. And one very familiar method is the path integral method. And the Hamiltonian, of course, should be a well-defined object with which is Hermitian and has an energy that's bounded from below. And then you can go ahead and define this. And we're sure that this will define a consistent thermodynamics. And we are also sure that we could also address non-equilibrium problems. You could take the same Hamiltonian and talk about time-dependent evolution of various statistical systems. So today I'm just going to focus entirely on the equilibrium problem, where there turn out to be serious issues on the black hole side, even for equilibrium. And what happens to non-equilibrium black holes is still a subject of some research, quite a bit of research. Anyway, so the way we normally proceed is we write this with a path integral of some fields, d phi, and then you have some action, which is a functional of these phi, and you divide it by h bar. So that's the first place that h bar appears. This is supposed to be a classical functional of some classical degrees of freedom, I. And I also has the form, typically, that it's going to be integral over some time, d tau, and then possibly an integral over space, d dx of some Lagrangian. And here, h bar appears in another place in the boundary conditions on top. So time, everything is periodic in time, and so you have to put this boundary conditions on tau to reproduce the partition function. Okay, and so this will be the Hamiltonian essentially, and then the integral of the it's not quite the Hamiltonian, but it's I don't know if there's a word for it. That is the Lagrangian. This is the Lagrangian density, and this is the full Lagrangian. Sorry. So this would be the classical Lagrangian, which is then integrated in time from 0 to h bar over kBt. And the fact that this is h bar over kBt, the h bar cancels with this h bar, and the kBt is over here. So in principle, the only places temperature and h bar appear are completely explicit. Okay. So if you could evaluate this path integral, you would have the full, knowing the classical action, you know everything, in principle. All right, so in gravity or black holes, what we do know is the classical action. And so we have kind of the inverse problem. We don't, even today there are arguments about what the Hamiltonian is, but we do know the classical action. And so we can at least formally define this. The only trouble is when we formally define this path integral, it's full of infinities. Now, we know how to cure infinities in quantum field theories, and so people have tried those methods here, and they don't work. So there's some very serious infinities, and so you could, at this point, just throw up your hands and say, this is not defined for Einstein gravity. So I'm going to take the Einstein action. So this is a functional of the metric G. And so it'll be, I'm going to work in 4-dimensional space-time. Well, let me say d3x and d tau. And d tau go from 0 to h bar over kBt. And the action is minus 1 over 2 kappa squared. And this quantity, which is the scalar curvature of 4-dimensional space-time. Okay, this is some complicated function of the metric G. Okay, so here I'm defining the metric, and just to make this volume invariant, you also have to put a square root of the determinant of G. And so here the metric is defined so that the proper time, ds squared, is G mu nu dx mu dx nu. Okay, so at this point, you might be getting lost and saying, well, I don't know what this scalar curvature is. I've forgotten. I learned it in graduate school, and since then I don't remember. And then I have to, so some get very complicated expressions. Well, I'm exactly in the same position. I don't remember what it is. But fortunately, now there are Mathematica programs that you can download. And you just give it some G, and it'll do the rest for you. It'll figure out the scalar curvature. It'll take the Euler-Lagrange equation, give you the equation of motion in any coordinate system you want. And so that's what I've done. That's my extent of knowledge of this. So from this, you look at the Euler-Lagrange equation of motion, di dg equal to 0, and you get Einstein's equations for gravity, where, let's see, so kappa, I have to tell you, kappa squared is 8 pi times the Newton gravitational constant. So in appropriate units, this Newton constant is very small, because gravity is a very weak force. And so it seems like there's a very small number out here. And so the prefactor is very large. And there's another very small number here, which is h bar. So it seems like some kind of saddle point approximation may be quite reasonable, because everything is multiplied by 1 over h bar g. And appropriate unit, that's a very tiny number. H bar g is a very tiny number. So, you might not worry so much that this path integral doesn't mean anything when I'm doing it for gravity. So I'm going to be interested in z of g, which is integral of all of e to the minus the Einstein action divided by h bar. Okay. So this is the path integral that we want to evaluate. But like I said before, it's not a well-defined quantity at all. It is not even clear, and even today that's a question of a great debate, that if I took the Einstein action in this way, is this a well-defined problem in the sense that I can invert this theory and give you a Hamiltonian? Is there a well-defined Hamiltonian for which this path integral gives the thermodynamics? The reason you want a Hamiltonian is because then you can address many other questions like time-dependent phenomena, not just the thermodynamics. And in fact, I think probably for Einstein gravity and maybe for many other theories, the answer is no in the strict sense. But nevertheless, this is a very useful thing to evaluate. And the current understanding, and here really I'm going out a bit on a limb, is that what often turns out is that this thing by itself is not a very well-defined object in the sense that there is no Hamiltonian here. But what people are now understanding is that if you just focus on the low energy structure of this and don't evaluate it fully exactly all the way up to the Planck scale, if you focus on some semi-classical approximation of this theory, what you're going to get is an ensemble average over a whole family of Hamiltonians. And that's exactly what nicely set up for the SYK model, because that's exactly what we're doing. We're taking the SYK Hamiltonian with some couplings Ui, J, K, L, and doing a whole ensemble average. And that ensemble average is pretty much shown, as I'll show in the next few lectures, to be a well-defined gravity path integral of this type. Yes? Yeah.
Why is the z, what's the z actually a function of? You wrote it as a function of g, but
The z itself, well, so for this talk, it's a function of temperature. Oh, thank you. Sorry. Yeah, it's a function of temperature. So once we know z is a function of temperature, then you can do, you can also, in principle, z of t is 0 to infinity dE of e to the minus e over kVt. So this problem I was stating here, given a path integral, can you give me a Hamiltonian? is exactly the problem here. Given z of t, can you give me a d of e? Now, this involves an inverse Laplace transform. And as you know, inverse Laplace transforms are very ill-defined objects. In other words, very tiny changes in d of e will give you hardly any changes to z of t. And so the question is really, is there a well-defined d of e which gives you the z of t at all possible temperatures? No, I'm not going to answer that question. But what we're going to address is the low energy and the low temperature behavior. And now the question is there a well-defined and sensible d of e that gives you z of t at low temperatures? And the answer is yes. For charged black holes, we now know the answer is yes, and we can actually even work out the precise form of d of e. Okay, and what the role of this ensemble average is something that maybe later on we can discuss a little bit, but it's intimately connected to this, in the current understanding, to quantum chaos, that often in chaotic problems, it's useful to take an ensemble average. Even for the quantum billiard problem, if you want to say anything about it, you can say something about and the distribution of energy level spacing and relate it to an ensemble average of a random matrix. That doesn't mean you're studying a problem that has disorder in it. It's just that disorder problems are often simplify things a lot and allow you to say things that you weren't able to solve in a problem without disorder. And this is a trick, actually, that Antoine and I had many discussions of in the early years, and it's now becoming, a central focus of a lot of this work. Okay. But I'm getting ahead of myself. All right, so let's just do a calculation. And I'm just going to do for you the calculation by Gibbons and Hawking from the early 70s. Okay, so what Gibbons and Hawking did, they solved these equations, and they got some solution for a black hole. They plugged it back in here and said, well, whatever you get here, that's the answer for the partition function. So Gibbons and Hawking basically are going to they're going to say that the z is essentially equal to e to the minus the Einstein action at the saddle point value. Let me call it g bar. That's really all they're going to say. So you solve Einstein's equation that gives you g equals g bar. And we just plug it back in here. You evaluate this. You encounter a few infinities, and you wave your hands and throw them away. There was a lot, not as simple as that. They had to properly regularize this theory out at infinity, and I'll talk about that. And once you do it, you get an answer. Then once you have this action, well, we know, of course, that z is E2 minus the free energy over kBt, and the entropy is minus df dt. And this calculation, the sequence of calculation, will give us precisely Hawking's famous result for the entropy of a black hole. Okay, so I'm going to try to derive that for you now. All right, so the solution, so I won't go through all these steps, of course, but there's a very famous solution, the earliest solution of Einstein's equation that first had a black hole. So I'm going to do this in flat space, asymptotically Minkowski space, just to illustrate the various points. But to really properly define everything in here, you do have to put in some negative curvature out at infinity. But for the things I'm going to derive, you don't need it. And in fact, Gibbons and Hawking didn't do that. And they were just working in asymptotically Minkowski space. It just simplifies the algebra quite a bit. So what the solution obtained by Schwarzschild is the following metric. I'm going to work strictly in imaginary time, plus r squared d omega 2 squared, plus dr squared over v of r. So, this is a two-sphere, and r is a radial direction. So here's a black hole. This is the radial direction. This is the omega 2 direction. And then there's also time, imaginary time. And of course, Minkowski space would be V of r equals 1. But what the general solution that Schwarzschild obtained was V of r equals 1 minus m over r. OK, so that's the solution of Einstein's equations in vacuum. And if you go, r goes to infinity, if you go really far out, then V of r goes to 1, and you're back to Minkowski space. But as you're coming in, what Schwarzschild noticed was that there's a 0 of V of r. There's a point when r equals little m, which is now known to be the black hole horizon. I don't think he recognized that at that time. Even the word black hole came much, much later in the 60s. This was, I think Schwarzschild discovered this in the 1920s. And there were many developments since then which led to this being, actually the metric for, say, the black hole at the center of our Milky Way is presumably of this metric. And this little m here is not quite the mass of a black hole. To figure out the mass of a black hole, you have to, again, go out at infinity and look at the gravitational potential. And if you open your GR books, it gives you a relationship between the metric and the gravitational potential very far away. And you compare those two quantities, and then you find that the mass, the gravitational mass of the black hole, which I'll call capital M, is twice the Newton's constant over m times m. So it's proportional to the gravitational mass, but it's not exactly it. All right. So if out at infinity this looks fine, so now we want to zoom in to near the horizon, where r equals m, which I'm now going to call r0. Okay? So we look at the solution of Schwarzschild right at the horizon, or near the horizon. So, yeah, I erased the metric. No, I didn't. OK. So V of r, so another few remarks. So V of r changes sign at r equals m. And that, things are blowing up here. This thing is changing sign, which means in some sense time is running backwards, it seems. So things seem very singular, all good reasons to ignore this solution. But a lot of those problems are coordinate singularities. If you take a different coordinate system, there is no singularity at r equals r0. And that's the reason for believing if you're falling into a black hole, you will not see the horizon. You will not know that you're past the point of no return because there is no coordinate independent singularity in the metric, although it looks singular at that point. And that's similar to, if you go to polar coordinates, there's a singularity at the origin, but we know in polar coordinates there's no singularity. It's Cartesian coordinates. You see that not everything is just fine at the origin. And this is in that vein. OK, so there's a coordinate singularity, but let's anyway try to make sense of what's happening then when this is positive, just outside the black hole. So we're going to say the horizon radius is r0. R equals r0, which is m for the Schwarzschild black hole. And so now let me change coordinates to just outside the horizon, r0 plus y squared, and then see what the solution looks like. So if you just take the solution and you expand it near r equals y squared, this is what you're going to get. Some overall prefactor. It's v prime of r0 squared over 4 y squared d tau squared plus dy squared. So we have replaced the radial coordinate of the black hole by y. This distance, this is the horizon. This distance is y squared, at least in the r coordinates. And then the angular part, which we just replace at r equals r0. OK, so now we look at this, And we see this is very familiar, so there's some number here. This looks like y squared d theta squared plus dy squared plus r0 squared d omega 2 squared, where theta is v prime of r0 tau over 2. Okay, so you just rescale imaginary time tau by v prime of r0, and then call that theta. And the reason for calling the theta, these are precisely the polar coordinates of a plane, okay, where one of the coordinates is theta and the other is the radial coordinate. So this coordinate system leads to a picture of a black hole that you may have seen, where the geometry of a black hole outside the horizon is the geometry of a cigar. Okay, people draw these pictures, which are very confusing, but roughly this is what it looks like. So this is the time coordinate. This is tau, or theta, going around the circle. And this is the distance from the horizon, which is y. Okay, so we're just embedding it somewhere in three-dimensional space. I'm not showing the angular coordinates. So in imaginary time, the world seems to end at the horizon, at least when you're looking from outside the black hole. When you're working in imaginary time, space-time just ends and has the shape of a cigar. Okay. This is nothing but plotting Schwarzschild solution in bizarre ways. Okay, but if you now want to think in terms of this mapping here, we've learned that time, imaginary time, has to be periodic with period h bar over kbt. And this coordinate system, well, this could describe a cone. Not, you could take a plane where theta goes from 0 to 2 pi and make a deficit angle. You cut out a bit of the plane. If this was your plane, you cut out this little piece, and then you fold it back together, you get a cone. So if theta went from 0 to some 2 pi minus theta 0, so this is theta 0 is called the deficit angle, and you get a cone, and then there will be a real singularity at the origin. Now we know there is no real singularity, so Hawking argued, and Gibbons and Hawking argued, that this doesn't make any sense. You want the end of the cigar to be completely smooth. You don't want any singularity here, because the horizon is a coordinate artifact. And that's only true if things are periodic with period at 2 pi. So that tells us that theta, things are periodic when 0 goes to theta goes to 2 pi. But we also know that things are periodic with tau going from 0 to h bar over kbt. But theta is proportional to tau. So very simple algebra now gives you the famous result of Hawking, which is that the 4 pi t Hawking is, okay, now I've dropped factors of h bar up there, sorry, but you can put them back in, is v prime of r0. So that's really all there is to it. You just have to believe that the Schwarzschild solution is a reasonable saddle point in imaginary time, impose periodicity in imaginary time, and you get the answer for the Hawking temperature. Okay. Hawking obtained this answer by other methods before. This seems like just too unbelievable on its own, but because they had the confidence of other checks which gave exactly the same value, I guess. Anyway, the other methods also had some, subtle issues that were not fully resolved. But anyway, so this result is correct, as we know today, but it's really obtained from rather dubious methods. We're just taking the saddle point of a path integral in imaginary time, where the path integral is not well defined, and where you also nobody knows what the Hamiltonian is, even today, really. Okay, so that's the first important answer by Hawking, the temperature. But now we want to also get the free energy. Okay, so the z of t is equal to e to the minus f over kbt. So what we have to do is to take the Schwarzschild answer, plug it back into the Einstein action, and evaluate the free energy. Okay, and then from taking a derivative of the free energy, you can get the entropy. Okay, so let me just take you through that. That's also quite a beautiful calculation. Anyway, okay. And it gives you a very simple and amazing answer, the answer being that the entropy is proportional to the area of the horizon. Okay, so why is it proportional to the area, and why is it something so simple? Well, first of all, the metric we've written down here, like this metric, at least has one nice feature, that it's time independent. There's nothing, V of r doesn't depend on time. And that seems nice, because that means the integral over time is just an integral, and nothing here depends on time. And whatever the Hamiltonian is, it's something. It'll give you some integral. So this thing, you would then just naively guess for a time-independent integral is just equal to beta, which is beta now is 1 over t, times some number. So the naive guess would be, if I just take this particular metric, which is time independent, and stick it into the action. The only place time appears is in this integral, so everything is well defined. You can just do the integral, and you get an overall fraction proportional to beta. So we have I is equal to beta. Now from the basic identities, this is all written in these notes, which you can download in a more coherent order than I'm writing on the board. So the entropy we know, in this very simple approximation, the action is minus f over t, which is minus beta f, and the entropy is minus df dt, and through some simple identities, you can check that it's beta d by d beta minus 1 times the action. Okay. All right, so that looks fine. But I is proportional to beta. So we know that in this very simple argument that IE is proportional to beta, and therefore this tells you S equals 0. All right, so it seems like if I just take the bulk solution far away from any near the horizon in particular, I'm not going to get any entropy. The only reasonable answer, even if I'm able to make this term finite, is just 0. Okay, presumably, Bekenstein thought of that, and I don't know. I mean, I don't know the history of the subject. All right, so what's going on? Well, the point is that this argument on independence on beta, is a coordinate-dependent argument, and it works everywhere the coordinate system that we're using is well defined. The more formal word is there's a time-like killing vector, and as long as you can define a killing vector, this makes sense, because the killing vector gives you a Hamiltonian that you can get from the action. But right at the horizon, just like the origin of polar coordinates, there is no theta-like killing vector. There's no direction. The angular direction is ill-defined right at the horizon. So there is something happening right at this point, even when you have a full circle, because there is no sense in which you can define a theta direction or a time direction. You can define it everywhere, but not at that point. So there is some singularity right at the horizon in the coordinate system, and that singularity will indeed end up giving a non-zero answer. Okay. All right, so maybe I'll just point to the slides here. All right, so what do you have to do? Well, first of all, you have to go slightly beyond the Einstein action. You have to introduce what's called the Gibbons-Hawking term, which is like a boundary term for the Einstein action. So you have to imagine, you have to cut things off at infinity somehow for these quantities to make sense. So Gibbons and Hawking argued that you should cut it off in a way that doesn't change the equations of motion. Okay? So I said earlier that you have some Einstein action, which is written somewhere. You have the Einstein action, so the I of gravity, and now I'm going to gravity in a region with a boundary. So I of gravity in a boundary is IE, but we're going to add a correction to it, which is the Gibbons-Hawking action. Now, if I just didn't have a boundary, we know that this gives us dE dG, gives us Einstein's equations. This is an infinite space. Okay, so this is how I started the whole lecture. This is what Einstein figured out, what the action was that gave Einstein's equations. But now we want to put a boundary. And inside the boundary, we want to do it in a way that these equations are still valid. It wouldn't make any sense to destroy Einstein's equation. We believe Einstein's equations. Okay? So, however, we want this to equal, so we want Einstein's equation now even in finite space. We just want ordinary Einstein's equation. And we want this to equal I gravity with a boundary. Okay, dG. Okay, so we would like this to be true. Now, even in ordinary classical mechanics, this is not always true, because you get surface term. You have to integrate by parts. So there will be corrections. For example, if you just had a free particle, then your Lagrangian, you have d tau times dx d tau squared. If this is your action for a free particle, then dE dx it has a term which is dx squared over d tau squared d tau, which is times delta x. No, that's dE. This is the derivative already. Well, I mean, not like this. So delta E, if you do the Euler-Lagrange variation, has a term which is dx squared d tau squared times delta x. So that's the term you like. But there's another term that comes from integrating by parts. So there's a term which is evaluated on the boundary of something like, well, it'll be just delta x times dx d tau or something like that. Okay. So this is the surface term. Okay. And that should also vanish. And in fact, it vanishes provided you choose appropriate boundary conditions. To get the Euler-Lagrange equation of motion, typically what you do is you fix the initial position and the final position, and you look at all paths that don't change the initial or final position. Then you're fine. You'll get the right equation, Newton's equation of motion. But if you put some other boundary conditions, you'll get extra terms. And so you have to compensate for that by adding extra terms to the action, boundary terms, so that you always get Newton's equations, valid for any boundary condition. Okay, so that's the famous Gibbons-Hawking term, which is chosen carefully so that this equation is true. Independent of the boundary condition, in the bulk, you will have Einstein's equation of motion. And this is an issue whenever you have second derivatives. And the scalar curvature certainly has second derivatives with respect to space. If you had first derivatives, this is not an issue. But it's an issue every time you have two derivatives. Questions? Okay. All right, so this is really elementary Hamilton-Jacobi mechanics applied to Einstein's equations. And from this type of argument, Gibbons and Hawking figured out what this term had to be to put a proper boundary on space-time, either infinity or at the horizon. And the answer is here. This is IGH, which I will write down on the board. And in fact, the entire answer comes from IGH, which is why we have to worry about it. Okay. So the Gibbons-Hawking term is an integral over the boundary of space-time, wherever it happens to be. And so this boundary has now one less coordinates, so d3x. This is space-time coordinates here, times the metric of space-time on the boundary, minus 1 over kappa squared, times this funny symbol K3, which is the extrinsic curvature of the boundary. So things seem to depend on the boundary and the way this boundary is embedded in four-dimensional space-time. So extrinsic curvature is the old curvature that Gauss figured out. The extrinsic curvature of a sphere is a product of the two second derivative curvatures. And later on, Riemann showed that can be defined, the intrinsic curvature is what Gauss computed as a product of the two scalar curvatures. And he also computed what's called the extrinsic curvature, which is the sum of the two. The extrinsic curvature depends on the coordinate system. It depends on how your manifold is embedded in a higher dimensional space. Now, Einstein's equations don't care are general coordinate invariant. Things shouldn't depend on the coordinate system. So these terms should not depend on the coordinate system. That's really the underlying problem, things we want to impose. However, when I take this derivative here for Einstein's action, I get terms that depend on the boundary and the way the boundary is embedded in the space-time. So I have to cancel that by this term, which it has to be exactly of this form, Gibbons and Hawking showed, depending on the extrinsic curvature, not just the intrinsic curvature. And that's chosen precisely so that these things don't depend on the coordinate system. Okay? All right, so that's the answer. And so now we just have to go ahead and evaluate this extra term, because as far as the entropy is concerned, this gave us 0, because this gave us minus beta h. And so now we just have to evaluate the Gibbons-Hawking term and see what it gives us. Okay? All right. So I know this is all very unfamiliar to you, but it's really an amazingly beautiful calculation, and it's not that complicated. And it took me a while of reading too many papers to distill this, so hopefully you're finding it useful. Okay, so now you just have to go ahead and evaluate this boundary term, plus at infinity, you just take my word, it doesn't do anything, but also at the horizon. There's a Gibbons-Hawking term. You also have to put it at the horizon because there's a coordinate singularity at the horizon. Or another way to say it is that, we know the rest of space doesn't give you anything. So you may as well move the boundary of your space-time right near the horizon. Anyway, so we want to evaluate this in this cigar geometry. Okay. Just in this region. So we are going to take the surface here. This will be a boundary. We're just going to evaluate in this little region here where we have this universal metric. And we're going to evaluate here I Gibbons-Hawking on this little surface. Okay. And is there power coming in? Okay, this is going to take a while. Okay, so now I have to do this in my head. I don't think, there, it's going to rescue me. So when you evaluate this, okay, let me see. Yeah, it's coming back up. Yeah, so these are the formulae that I do not know on the top of my head. Even what the extrinsic curvature is. Yep, okay. Maybe I will just go ahead and start writing it out, just show you the answers over there. Okay, so we're going to evaluate this IGH term right at the horizon of the black hole. Okay. Okay, right. Oh. Right. So now there's another very useful formula. You don't have to look up what the extrinsic curvature is in general. These are things I did a couple of years ago in great detail. But anyway, there's a general formula. In fact, this is how the extrinsic curvature is defined. You choose what are called Gaussian normal coordinates, where n is the coordinate normal to the surface, and then you just take the derivative of the area or the volume of the boundary. Just compute the volume of the boundary as embedded in the higher dimensional space and figure out its derivative with respect to the normal coordinates. All right, so we've taken this little region here, which is y equals epsilon. And the metric, if you remember, was extremely simple. It's some constant here, which actually you can scale away. It's y squared d theta squared plus dy squared. And there's also r0 squared d omega 2 squared. So the first thing when you evaluate this area is that when you evaluate this volume, there's 2 dimensions of the omega 2, the transpose coordinate that are not even shown here. This point is really a sphere of radius r0. Okay? So these transpose dimensions will give me a factor of the area, which is this thing here. So the integral square root of g boundary of the extrinsic curvature, of just the volume of d3x over the boundary will give me a factor of the area. And then I have to figure out, now, y is my normal Gaussian normal coordinate. Y is just like n. So I'm going in the direction y. So I'm going from 0 to y. I'm going from y to y plus epsilon. So y to y plus epsilon. So the volume of this little region is the circumference, which is 2 pi in the theta coordinates, and then an epsilon. Okay. All right, so you put it all together, and you get this 2 pi epsilon e. Then you take the derivative. Oops, what's going on with this mouse? Oh, sorry. Here we go. Yeah, you get this 2 pi epsilon e. Then you take the derivative with respect to n, which is the same as derivative with respect to epsilon, and there you get the famous answer. Okay. So the answer, when the dust settles, comes from this boundary term, and because the boundary is right at the horizon, you get a factor of the area. So it's only coming from the surface area of the black hole. So finally, I have the other important result, in addition to Hawking temperature, that the entropy is 2 pi times the area, the 2 pi coming from the circumference of that circle. There's a factor of kappa squared in the definition, and so that gives you, in the end, the area divided by 4 g Newton. Okay. The h bar and kb have disappeared. Yes. So if I remember right, there's a c cubed, and this is s over kb, and there's an h bar here. Okay. And I don't remember the factors right here. Okay. So that's basically the square of the Planck length, gn times h bar over c cubed. All right, so that's the, basically what's in the original Gibbons-Hawking paper. I mean, I tried to read the paper, it's totally incomprehensible. Then later on, there have been various lecture notes that I've read, and talked especially to Gary Horowitz, and this is a simplified, cleaned up version of their derivation. If I could do better, and really I think my understanding is no one really knows how to do better. This is what you have to do. There are, you have to take in faith that their method of putting a boundary makes sense. I mean, it really does make sense because you want to preserve Einstein's equations. And once you accept that, this is the answer that you get. All right. Okay, now this particular answer is, if I would like to know in general for a black hole in 3+1 space-time dimensions, what are the corrections to this? In particular, this is the saddle point answer. Can I go beyond the saddle point? Can you give me a density of states? Can you tell me, does this make sense? And what are the corrections to this beyond the leading saddle point answer? Does it make sense for an evaporating black hole? I think these questions are just generally not being answered today without the help of supersymmetry, but then you get other artifacts that maybe I'll mention later. However, for another type of seemingly more complicated black hole, there have been a lot of answers. And that's the second solution I'm going to discuss now. And that's the case of a charged black hole. So this is very much the same calculation. The equations are a little more complicated. But the ideas are exactly the same. And in fact, in the original Gibbons-Hawking paper, they also stated results for this case. This is called the Reisner-Nordstrom solution of Einstein's equation, which was obtained a bit later by Reisner and Nordstrom, I guess. And now we are working with the action, not the Einstein action, but the Einstein-Maxwell action. Okay, so we take ordinary three-dimensional gravity, d tau. You have the scalar curvature in 4 space-time dimension divided by 16 pi g Newton, plus, I guess for strange reason, I call it g sub f, but this is just the electric charge, g sub f squared of the Maxwell action, where f mu nu is d mu a nu of some gauge field. Okay, so you take the vacuum Einstein's equation and the vacuum Maxwell's equation, and you solve them with spherical symmetry. And this turns out to be an exact solution in any dimension, and that's the Reisner-Nordstrom solution, which I've written down over there. So the solution of the vacuum equations.
The only way the proton couples to the gravitational
Exactly, right, which I forgot to put. Right. Yes, right, yeah. So the electric field, as we'll see, has a stress energy tensor, and that will appear on the right-hand side of Einstein's equations. Yeah, so that's it. There's no other coupling to gravity. That's true for anything, any matter, or any other field. It just couples through the metric tensor, the volume of space-time in this case. Okay, so the solution of the vacuum equations you can figure out, and the metric looks exactly the same form as before, which I have erased. Let's see if I remember that. V of r dr squared plus r squared d omega 2 squared plus d tau squared over v of r. I got that the right way. Okay, and there's an electric field, a radial electric field, which will be minus the gradient, d by dr, of the time component of the vector potential. So there'll be an electric field going out. So the picture now is that in addition to having a mass at the center of the black hole, there's also some charge. So you have some very dense mass and charge here. And here's the horizon. So space-time is curving, but the charge, we can figure out the electric field very easily. It has to be an electric field, and it has to be given by Gauss's law, 4 pi q over r squared, or something like that. 4 pi r squared. that's just Gauss, that's the electric field everywhere, because outside the singularity of the it's not as simple as that, I guess, because this maybe factors the metric. Yeah, so let me be a little more careful. What is true is that the scalar potential is very simple. So A tau, which is the scalar potential in imaginary time, it's imaginary, but not the electric field, but the potential is given by Gauss's law. So we take A tau is I mu times 1 minus R0 over R, where R0 is where the horizon is, and Q is related to the this is Gauss's law, it's 4 pi mu R0 over GF squared. Okay, that's just Gauss's law. All right, so there's a electric field going out, and space-time is curving, and there's a horizon. Okay, and now V of R is a bit more complicated. I won't bother writing it out. There is a V of R in the first equation here, which is this V of R. Whoops. Okay, so this was the old solution when M was, when there was no charge, and now there's an extra term, theta squared over R squared, and this is where the electric field is making a difference to the space-time metric, and vice versa. I mean, they're coupled to each other. It's a self-consistent solution. Theta is proportional to mu, which will be the chemical potential, which we define as the value of the scalar potential at the horizon. No, sorry. At infinity, at the horizon, the scalar potential is taken to be 0, and the charge is proportional to the chemical potential. And the entropy is the same formula as before. All right, so you get some complicated solution, and from which you can then figure out the free energy and the entropy in exactly the same way as before. And now the free energy is a function of the charge and the temperature. Okay? And I've given you all the expressions. The algebra is more complicated. I gave you the entropy. I've given you the charge, and you can figure this out. And you can also, from this, figure out, of course, the chemical potential. Mu is dF dq at fixed temperature, and the entropy is minus dF dt. Okay. So these are things you can solve and work it all out. Okay, just I think things were not written down until much later by, especially a paper by Shamblin et al. With Rob Myers and others in general, what these functions are. But, you know, it could have been done already at the time of Schwarzschild. It's really nothing more complicated. It's exactly the same calculation. So roughly speaking, what's happening here is that you have some charges, and they're all repelling each other and want to explode. But there's also gravitational attraction, which is preventing them from exploding. And as long as the gravitational attraction is stronger than the electrostatic repulsion, this is a stable solution. But you can't make the charge arbitrarily large. In fact, here the charge is very, what you find then, if you want to make a temperature low, you have to make the charge just at the boundary where it's just about to explode. And that's what's called an extremal black hole. But I think as a condensed matter physicist and not a gravitational physicist, I'm just interested in this function f of q and t and its properties at low temperature for a fixed charge. Okay, and that's like taking the extremal limit where it's just about on the boundary of stability. Now, you know, it's almost certainly the case there's no such black holes out there. Anytime there's a net charge, you know, the oppositely, the universe is neutral, and other charges will come in and neutralize it. So that's too bad. But anyway, okay. So you solve these, you know, I've given you everything on the board, really. You can, on the screen, and you can go ahead and solve all these equations and get f of q and t. And the amazing thing is these equations have many properties which are very, very similar to the equations that Antoine was just showing you for the SYK model. So the first thing you find and I don't know who discovered this first, I think it goes way back, is a zero temperature entropy. So here you go ahead, solve these equations, figure out the entropy as shown by Bekenstein and Hawking, and the temperature. And the thing you find now is that this equation V of R is non-monotonic as a function of R, this equation right here. So the horizon is still given by V of R equals 0. But you see now, if you want to take the temperature to 0, you not only want V of R equals 0 at the horizon, you also want V prime of R to be 0 at the horizon. Now, for a Schwarzschild black hole, there is no such point. You can't take the temperature to 0, at least for asymptotically Minkowski space. But for a charged black hole with asymptotically Minkowski, there is such a point. There is a solution where you can take the temperature as small as you want, provided you're at the quadratic minimum of V of R, and that's the point where it just touches 0 at the same time. So there is a solution. You fix charge, and you look for a solution as temperature goes to 0, and you find a solution where the horizon radius is finite. So even at 0 temperature, the horizon is there. It doesn't disappear. Okay, this is just a property of the Bekenstein-Hawking formula. So you can go ahead and compute the entropy, and you get some answer. You get a 0 temperature entropy. Of course, this number has nothing to do with the SYK model, but the number that Antoine gave you a prescription for. This is a property of, it's a UV sensitive answer in the sense that it depends on Newton's constant and the horizon radius, which depends on the electric charge and so on at 0 temperature. So it's just some number, which is given by the area of the horizon at 0 temperature. Okay, so that's good. But then you also look at the first correction. This is just a property of Einstein-Maxwell's equation. Then you find that there is a linear and temperature correction. So this is something Antoine has not told you about. He mentioned at various points the corrections to conformal invariance that I will say something about next lecture. And in fact, those corrections were not known to us in 2000 when we wrote our paper on the 0 temperature entropy. They are now known and been checked in great detail, and that came after the gravity solution. In fact, the SYK model has also this linear and temperature correction. And being a solid-state physicist, I call the coefficient gamma. This is just like the gamma specific heat of a Fermi liquid. Specific heat is gamma T, which is also true here. The specific heat is ds dt. So for the specific heat, the S0 doesn't matter, and you get a linear and temperature specific heat. And this number gamma depends on all kinds of details of the solution. Okay, so the rest of I guess I'm already out of time. Yes. Next lecture, I guess I'll have to finish this logic argument. What we'll find is that the theory that determines this correction and even the next correction. So you notice the terms here are so you have the entropy, which is 1 over g times some constant plus another constant times t. And then we are also, by the end of next lecture, going to talk about the next term, which will be of order g. This is for small g. The next term will be ordered to the g0. This is actually known now. What is the correct term? And this term is exactly the same for the SYK model and charged black hole. It's fully determined by actually these numbers over here. You also get the next term. And that comes from doing the path integral. So far, I haven't done any path integral. The saddle point gives you the 1 over g term. Next, we're going to do the path integral in the low temperature limit. And a sector of it can be done exactly, amazingly. And that gives you then, in gravity, the next correction of order g to the 0. And in the SYK model, correction of order n to the 0, where n, the leading term that Antoine showed you was the dependence on the number of particles. So there's a 1 over n correction, which is now also known. And those corrections are given by the same theory. Okay. All right, so now the task is, let me just say a few more things. Why are these things universal? And also make a connection to something else Antoine said. So let's take this metric, this Reisner-Nordstrom metric, and play the same tricks as we did for the Schwarzschild metric. So here's a rather complicated metric with this V of R looking really like a mess. Well, now we're going to zoom in at 0 temperature to the vicinity of the horizon. So previously I had said, R was the horizon, R0 plus y squared. Now I'm going to choose a different coordinate system. I'm going to say it's RH plus RH over zeta squared. It'll become clear why. Not zeta squared, zeta. So that the horizon is at zeta equals infinity. Okay, so you have a horizon at zeta equals infinity. So you just make this change of coordinates and look at what the near horizon metric is. Very close to the horizon and very far from infinity. And then you get this universal metric. So there's the angular part as before. But now, instead of getting the metric of an infinite plane, so-called Rindler metric, here we have the metric of anti-de Sitter space. It's not an infinite plane. It's a surface of uniform negative curvature. So this metric here is called ADS2 in a different way. Let me show you here. So this is how you may have seen it in the famous pictures by Gödel. It's a uniform negative curvature in a slightly different coordinate system. So this is the metric I was showing you. Then you go to coordinates rho and theta tau hat. And now time is explicitly a circle of period 1 over temperature. And the radial coordinate here is this rho, which is related to zeta and tau in some complicated way. Anyway, and this is a homogeneous space. In particular, any point is the same as any other point. In fact, in this metric, if you look down here, if you replace the sinh squared rho by a sine squared rho, that's the metric of a sphere. So a sphere, we know, seems to have some singularity in theta phi coordinates, but it doesn't. There's no singularity at all. And the metric of a sphere is d theta squared plus sine squared theta d phi squared. You just replace the sine by a sinh. You get, instead of getting positive curvature, you get a negative curvature. It's an infinite space with uniform negative curvature. And you can't find any horizon here because the horizon is a coordinate singularity anyway. So what happens is that you get this very different metric for a charged black hole. And what's very nice about this metric, to just connect up, is that it has a conformal symmetry. You can make a change of coordinates of tau prime plus I zeta prime goes to this. And this change of coordinates will not change the metric. So the metric in the tau prime and zeta prime coordinates will be exactly the same. And in fact, for the SYK model that Antoine talked about, you have to think of that as, in the boundary of space-time of ADS2, which is, say, at zeta equals 0. I'll talk about a bit about that next time. This coordinate singular, this transformation, tau prime equals A tau plus B plus C tau plus D. This is also an invariance of the saddle point equation that Antoine discussed. He was using slightly different coordinate systems and finite temperature. You can also generalize this to finite temperature. Anyway, so this symmetry of ADS2 is exactly the same symmetry as the symmetry of the saddle point equations that Antoine was using to get the conformal structure of his answers. And that symmetry is really the fundamental link between the two problems. And that part was pointed out by Kater. I had many years earlier pointed out that there was a connection between these two problems, thinking more about the entropy and the conformal solutions that Antoine had shown. But Kater made the explicit connection once he understood the time reparamerization symmetry. Okay, so Hopefully now you get some sense of, maybe I'll end with this picture of what's going on here. So you have a charged black hole, which is sitting here. This is the coordinate zeta. The horizon is at zeta equals infinity at 0 temperature. If you look at it at finite temperature, very low temperature, zeta equals 1 over 2 pi t. And in this near horizon region, you have the transverse direction, which just factorizes. But if you're unlucky enough to be falling into this charged black hole, well, the world would look to you like it's one space and one time dimensional. So you would just be aware of the ADS2. You'll be falling along a line. But then you'll be very fortunate because quantum gravity is simple in one space and one time dimensions. So at least you can work out the quantum corrections of what's happening to you as you fall into the black hole. And that's what I'll talk about next time. So it turns out, just like in the Gibbons-Hawking calculation, the entropy of ADS2 only depends on the boundary. In this case, the boundary is somewhere here where space-time is changing from 1 plus 1 dimension to 3 plus 1 dimension. And there are some dynamical boundary graviton degrees of freedom. And those boundary gravitons, I will derive next time, if I time things right, in two ways. There's an action for the boundary graviton, which you can derive it in two different ways. One way is you start from the SYK model, and you do a careful analysis of the 1 over n corrections. The other, you start from Einstein gravity, and you do a careful analysis of the order g to the 0 correction by doing the path integral over Einstein gravity. And you get the same action for the boundary graviton. And that's what leads to all these similarities. And the reason you get the same answer, ultimately, is because of symmetry. It's because of this symmetry here, this SL2R symmetry. And that's obeyed by the saddle point of gravity, which you only have for the charged black hole case. You don't have it for the Schwarzschild case. OK, I'll stop there.